Hello, my name is Michael Watson, and for my material I picked copper. To understand how copper has impacted our world and its properties, we first need to look at its history. It was said to be discovered around 9000 BCE. Many people believe that this early discovery is linked to the fact that copper can naturally occur in relatively pure forms. It was not until around 5000 to 6000 years ago that the Mesopotamians were fully able to extract and use copper. From this, society was propelled into the Copper Age. Since pure copper is a soft metal, early societies did not use it for tools or weapons, but instead used it for decorations and ornaments. Also, when copper is weathered and oxidized, which I will talk about later in the video, it produces a very visually appealing green tarnish color. Eventually, the Bronze Age was reached by the Mesopotamians, and they could now create an alloy of copper called tin and bronze. Bronze was much harder than copper and therefore could be used in weapons and tools. Even when the Iron Age came about, the use for copper did not stop. The demand mostly came from coins used as currency, and the new alloy from copper and zinc called brass. Copper coins were brought in as currency by kings in the now named European area. Copper continued to be used throughout the rest of history, especially in today's world, although there are many alloys, for all kinds of things including circuits and pipes. Moving on to copper's properties. Copper has a face-centered cubic crystal structure and is overall pretty ductile. Copper can be formed and stretched into complex and intricate surfaces without breaking. This makes it possible to create spires, steeples, music instruments, bowls, bed frames, tubes, and a huge number of other useful and beautiful products. The very small diameter wires which transmit power in cars, computers, televisions, lighting, and mobile phones only exist because of the high ductility and malleability of copper. As of right now, copper has a melting temperature of 1083 degrees Celsius and a modulus of elasticity of 48 gigapascals at room temperature. Its modulus of resilience is 829 psi, and its yield strength is around 160 megapascals. The current price per kilogram for copper is around $7.60. It has a density of 8.96 grams per centimeter cube, and its primary bonding is in a metallic bond. On the right, you can see a picture of copper under an electron scanning microscope. Next, let's take a look at how copper is produced. The production of copper first starts with locating it within the Earth's crust. We can do this nowadays by using a simple helicopter area survey combined with a detailed and small-scale drilling of the area of interest. This combo will show if there is enough elemental copper to begin building a full-blown excavation site. If enough is found, the rocks and the ore must first be loosened up by either blasting or grinding equipment. After the ore is loosened from the surrounding rock, it is separated with the use of machines and transported to the processing refining plants to remove the remainder of the impurities from the element. There are two types of copper processing because there are two types of elemental copper. They are sulfide copper ore and oxide copper ore. Sulfide copper ores are typically put through a crusher machine that reduces the rocks down to about 7 to 8 inches long. From that, it goes to a secondary grinder machine that further reduces the size of the rocks. Lastly, the rocks go through a wet grinding process involving water and steel balls to reduce the ore and rocks to a very, very small size. With oxide ores, it goes through the primary and secondary grinders, but does not go through the wet grinding process. From here, it goes through a couple more processes in order to reach the purity needed to be used as an electrical equipment. The most widely known and recognized use of copper today would be in the electrical field. This accounts for over 50% of all uses of copper in today's world. Whether it's transformers, transmission lines, copper traces on a PCB board, copper is almost always the material used to allow the flow of electrons on a device. This is because copper has a very high level of conductivity, aka its resistance is very low. So almost all of the electrical energy transferred through it will reach its destination without producing too much heat. Copper also has a high resistance to corrosion, which again makes it a very good candidate for transmission lines since they must endure years of rain, snow, and high winds. Now we know that copper is actually used in our body and is involved in many natural processes to keep us functioning and healthy. With that said, I wouldn't go out and start eating the metal, as only 10 milligrams can cause kidney failure and death. Even with this in mind, we still use copper pipes to transport water. Why? Wouldn't we start experiencing side effects from its diffusion into the water? Well, actually not. It's because copper contains antibacterial properties and the rate of diffusion of copper is also extremely low. I will talk about this later on in the video. Another use of copper in today's world would be computer heat sinks, such as the one shown in the picture here in the top right corner. Copper has a very high thermal conductivity value, which allows it to transfer heat very effectively. There are actually nutritional supplements out there that have copper in them to help support healthy organs in a person. But as I said before, you have to be careful on how much you take because you could reach a lethal dose very quickly. Another use of copper today is in shipbuilding. Copper has a very high resistance to corrosion, as I stated before, from water, as I will discuss in the next slide as well. This makes constructing the hull of a ship out of it ideal. Lastly, copper is used in many musical instruments. These include trumpets and trombones as well. As for corrosion of copper, it is done by what is called oxidization. It is where a metal, copper in this case, loses or gives up its electrons. Oxidization of copper can be caused in the presence of water or carbon dioxide. Both of these chemical makeups can oxidize and degrade pure copper and cause it to turn a blackish brown color and then eventually turn green, sometimes blue as well. Oxidization can occur most commonly on the surface in what is called uniform corrosion, which you can see in the bottom picture there. But it can also go through non-uniform corrosion. This is where oxidization happens in a specified area on the material, and it is especially bad for copper pipes as it is easier to cause small leaks when the corrosion is more focused in an area. By using the corrosion penetration rate formula, you will find that copper has a very low corrosion rate when it is used to transport water. Just plain soft water will only corrode at a rate of 12.5 micrometers per year. This means given a pipe with a wall thickness of 0.7 millimeters, it would take almost 50 years in order to have enough oxidization to breach the wall of the pipe. If it is simple drinking water, the CPR is only 2.5 millimeters per year. This means a 7 millimeter pipe could transport drinking water without fracture for over 250 years before needing replaced. Moving on to copper's electrical properties. Pure copper is most notable, and its most notable and most important properties are its electrical properties. In terms of electrical resistivity, copper comes in at a very low value of about 1.7 times 10 to the minus 8th. In contrary, this also means it has a very high electrical conductivity. Electrical conductivity is the ease at which a material is able to conduct an electric current. Both of these properties are in copper because its outermost energy band is only half filled. Copper's electron band structure has available electron states above and adjacent to the filled states in the same band. This means that electrons can come and go, aka flowing current, more easily than in other materials due to all of these free bands. Flowing current in any material is just the movement of free electrons. Copper is able to move more of these free electrons at a time than other most metals, and this means that its current density is very high. Ultimately, it means that more of the generated power from a source can reach its destination without being turned into heat instead, aka wasted power. But for an electron to become a free electron, it takes energy. Once again, copper comes out on top due to its available electron states above and adjacent that allow for a very low required energy to push these electrons to become free. With the ability to move many free electrons at once, copper also has some drawbacks. When an electrical field is brought within range of free electrons, or makes them, It exerts an electrical force on the electrons in that direction that it's going. This would make the best conductor in the world if that's the whole story. Unfortunately, due to material impurities, even the 0.001%, vacancies in the unit cells, and even the thermal vibrations of the atoms themselves, these free electrons can scatter, lose their kinetic energy, and eventually change direction. Thus, the more impurities and defects in a copper wire, the less conductive that wire becomes. This process produces a sort of friction force on the current. This counterforce depends on two factors, electron mobility and drift velocity. Drift velocity is the average speed of an electron that has changed direction to go against the force of the electric field. Electron mobility is a measure of the frequency of the scattering events happening within the copper. All of this combines to explain the reason why dropping a magnet through a copper pipe will take more time than through an insulated pipe of the same length. Every electric field will produce a counter-electric field and a conductive material. Temperature also plays a large role in this identified counter-friction force. As temperature increases, the electrical resistivity also increases linear with it. This is partly why computers have fans on them. Copper tubing is actually used as a heat transfer for the CPU and GPU. If these units get too hot, the resistivity goes up in the copper traces on the PCB and inside the processors. This ultimately slows down the rate of current, which reduces the max power output that it can make. The last big player in increasing resistivity is plastic deformation. Stretching copper past the linear region will cause more impurities and vacancies within the material, thus causing increased opposing electric field forces when current is transferred through it. And that concludes my video on copper.